Welcome. This is another Wolfram Institute Community Forum. You'll have to excuse us. We're in a somewhat peculiar situation this week. I'm very sick. I have some respiratory issue, which is affecting the quality of my voice. Carlos actually lost his voice. Um, Nick is not even in attendance. I presume that Nick is preoccupied because currently we have the Wolfram Winter School in session. So we have a number of students who are studying physics, mathematics, economics, computation, even chemistry with us at the moment. I'm involved with many student projects, maybe over 10. Łukasz and Carlos are also involved to not to as considerable an extent. And Nick and I have spent most of our time recently just meeting with students. So I imagine that Nick is preoccupied debugging someone's code or putting out some sort of computational fire, so to speak. So, but the show must go on. We must continue anyway. So I think what we're going to do today is Carlos, Łukasz, and I have been involved in some recent philosophical discussions about computational theories, especially computational theories of physics or mathematics. Maybe you'll call them meta theories. That's neither here nor there. But discussing those within the context of areas in the philosophy of science such as naturalism, constructivism, reductionism, um, and these kinds of topics. I thought that we might kind of continue it and maybe solicit some of Carlos's opinions, Bukash's opinions. In Carlos's case, he might have to type the answers because his voice is somewhat restricted. I'm guessing he'll actually type it not in the Zoom chat, but in the chat for our streams. But I might also read them, or Wukash will read them. Um, Also ask Wukash his opinions of things. Well, so one thing that we've been discussing is there's this notion of naturalism in philosophy of science, and I'll give, a very kind of elementary, very simplistic kind of definition of naturalism is that you should be able to explain natural behavior with natural explanations and not rely on any deus ex machina, any supernatural explanation that falls kind of beyond the realm of nature. It's very, very kind of simplistic description of it. And I've been contemplating the relationship between naturalism and maybe this kind of philosophical persuasion that I might call computationalism, which is maybe kind of a constructivist theory of physics, or this notion that um, natural processes themselves can be understood to be computations, and that explaining natural phenomena could be simply a practice of finding particular rules or finding particular algorithmic constructors that give rise to their behavior. I've been kind of contemplating the relationship between that and naturalism. And so, what do I mean when I contemplate the relationship between that and naturalism? I suppose what I mean is um, taking a kind of a critical audit of the kind of work that we're doing at the moment. Um, can is there any kind of deus ex machina that we rely on? Is there anything kind of outside of the theory itself that we can't explain? How can we kind of account for it? So Łukasz will have his take, but Carlos, there are kind of two things that I brought up that I feel as though we still can't explain. So you take a scenario, suppose that we find a nice constructor that really seems to give rise to um, that under the right interpretive framework seems to give rise to emergently some sort of physical system that has the right properties that we're looking for. Nonetheless, even identification of that constructor doesn't explain two things. The first thing is you have some sort of a constructor, it's some sort of a rule. That rule still has to get executed. It still has to get computed. You still have to have kind of evolution and dynamics in your universe. And it's not clear where that comes from. There's this theoretical computer scientist called Manuel Blum, and he once asked Stephen, actually, or he asked some people in a meeting, in a call, Stephen was there, what puts the fire in computation? What makes it so that computation actually runs, so to speak, in a kind of abstract sense. And that's something to me that it's not clear to me what the answer to that is. So maybe you find some rule which, when run, happens to give rise to physics as we know it, but what makes it so that that thing actually gets run as opposed to it just being some abstract rule, some abstract set of instructions? This could also be perhaps reduced to a question of, why is it that things are realized or actualized in time, temporally, as opposed to just being possibilia? And then the other question is, why are there possible rules? Why are there possibilities at all? So maybe you can say you could take the Ruliad, or you could take all possible constructors. You can consider which ones give rise to our universe, but that requires the a priori existence in some sense of these different constructors. But where do they actually come from? Why is it that things are actually possible to begin with? Or is it even tenable for us to speak of constructors a priori? Um, what grounds do we have to even suppose certain things to exist in an a priori way? Because we don't really have access to it. So those are kind of two things that it seems as though we don't actually have a way to explain it, that we kind of rely upon. And of course, um, people do sometimes ask questions related to this. Like, we'll get questions where people say, okay, so if there's a rule that's going to give us most of physics, does that mean that the universe is a computer, or what computer are we running on? Is this a simulation, et cetera? And I think that those are kind of slightly less abstract recasting of the same question, which is, you find a given algorithmic constructor for a physical system, but why is it that thing is computed? And also, where does it actually come from? So these are not easy questions, but these seem to be two kind of limitations. And I think Nick had some responses of how to think about these things, but I thought that I'd ask Łukasz and Carlos for your thoughts on this. Łukasz, not to put you on the spot, but you're going to be able to respond more quickly than Carlos.
Like, what ontology we actually subscribe to? Like, do we need to assume that rules exist in this Platonic realm? Because, like, for me, compute this computation works and also of that, but computation is really the model of human thought, not not the actual universe itself, but the universe as we can perceive it.
Yeah.
Like, all aspects of the universe we can perceive can be represented as computation. And universe itself may be not computational. Like, there may be this Lovecraftian parts of universe that are not computational and therefore will be like incomprehensible to us.
Yeah, I mean, we've discussed this in the past. I mean, it's something that I do fear, which is, um, oh, well, because if Carlos is asking, well, what would an answer look like to me? Well, to provide a definitive answer to this difficult question seems to be, it would be maybe somewhat brash, but I do want to entertain this line of reasoning that Łukasz was kind of hinting towards, which is one thing that we had discussed previously is, um, okay, so humans are kind of bounded organisms, and we have certain ways of phenomenologically processing things. And for much of my life, I've kind of feared that even our notions of physics, et cetera, are kind of artifacts that are highly influenced by the way in which our own sensory and cognitive apparatus are are processing what could be more complicated or sophisticated um, exterior stimuli, much of which we can't access. This is something that I have feared. This is the kind of thing that Lovecraft would push you to consider. I mean, one thing is that we've been kind of lucky as a species in that we've invented computers and neural nets, and we've kind of built this computational paradigm, which seems to, in many respects, um, emulate or at least mimic, sometimes in quite different ways, the way that the human mind works. And eventually, we might be quite sophisticated in mimicking the human brain. But our species is still quite young, especially on the technological front. And it's like, I don't see why we shouldn't suppose that the greater, I don't know, greater universe or physical system beyond what humans could capture has aspects of it that are more complicated that could only really be analogized. We could only draw an analogy between that physical system and technology if we had more advanced technology. I mean, we've only developed so much technology, so we can say, oh yes, this looks like computation, this looks like computation. But what if there is more advanced technology that we develop 2,000 years from now that then helps to explain other features of the universe that we can't properly detect at the moment? And what if it requires us with what do they call it in evolutionary biology? An expanded phenotype, like us expanding through other instrumentation our own senses so that we're able to actually pick up on other things that are happening in the physical system around us. So, yeah, so okay, so if we take this point of reason that Wukash is suggesting, then I guess the point is, right, it seems somewhat untenable to refer to these rules as existing a priori, right? It to say that there are certain computational rules, they have an a priori existence, and all we have to do is find those rules with a priori existence because those are going to give rise to our universe. It's more that I think to Wukash's point that computation seems to, in many cases, approximate or even emulate behavior as humans see it. But this is in part because what we see is itself a computation of some kind. So computation could be, in some sense, a very, very anthropic thing. Um, and that the ways in which we're going to model things computationally are also going to be bounded by our ability to actually make sense of them. And so in a sense that these are all just human observables. The kind of computations that we do, the technologies that we build that we can understand, the observations that we make. Nick, have you joined?
Yes, I'm here. Yeah, I
Hey,
joined.
Nick. We're discussing exactly what you think we'd be discussing, which is this whole naturalism, computationalism thing.
Oh yeah, the reason I slept too bad today because we discussed it yesterday for too long.
Yeah, yeah.
Right.
We were up wicked late with Lucas trying to figure this out. Well, so Wukash is pointing out this aspect that we discussed previously, but not last night, which is okay. So I asked the kind of basic question: Is it really acceptable philosophically for us to suppose the a priori existence of certain rules, or maybe even certain mathematical structures? Like, how can we defend it? How can we actually presuppose that these things exist a priori as fundamentals? And Wukash makes the nice provocation that what if computation is more of an anthropic focus that physics or the greater universe is not just computation as we understand it. Maybe we need more advanced, sophisticated technology in order to really understand how all of physics works, and that computation is just something that kind of agrees with our senses, perhaps because our own cognitive apparatus is not too different from computation, but that it's not actually right to presume that these things are these fundamental ontologies to which we should commit that are absolutely at the bedrock of reality. Maybe it's part of the picture, but maybe it's not. Maybe it's not complete.
Yeah, but my sort of point is that we don't need this more advanced physics, which is non-computational, because we wouldn't be able to comprehend it, like in principle. Computation models all we can think of. If you can think of something, then you can model it computationally. If there's something that you cannot model in any way, then like it's this Lovecraftian monstrosity, right?
I don't know. You don't think we could come to understand you know, you don't think with time humans could come to understand more intricate, difficult aspects of behavior and even create technologies around it.
I had this discussion with Lucas that like what if we found like somewhere in the outer space we found an object that when you take two of this and two of this and combine you get five of this. Will it like blow the human mind? Or would it be the case that by playing with it we would just eventually learn and develop some intuition about it?
Well, if it's the unique object that only does this, it's not it doesn't contradict anything that we already know. So it's really simple to adjust.
Like the class of objects, right? But then basic arithmetic breaks up, and
Well, it doesn't break. Well, it doesn't break because it's like just a different object that behaves some different law.
yeah, but
The laws itself are still computational.
yeah, but would we be able to comprehend this law?
Well,
This
why
is the
not?
point.
Well, maybe you have some stronger notion of comprehension. It's like, what do you mean to comprehend it? It's like you see the result, you're able to.
Wait, maybe I'll read the point made by Carlos. I have a similar mindset that computation is mostly anthropic perceived phenomenon. However, some facts about physics, such as the interchangeability of fundamental particles and the absolute nature of the apparent mechanism of causality, do give me an uneasy feeling that computation or information may be quite fundamental in naturalist sense. Yeah, but I mean, all the laws of physics describe the physics perceived by human beings, and yeah, basically that's what I mean. The computation is fundamental to that part of physics that we can perceive. So, for example, the particles that we perceive, yeah, that they are computational and this sort of stuff. But
okay, but there is something that, I mean, one obvious point to be made though is that to some extent we're speaking about anthropic limits, but humans are able to further expand those limits. I mean, even if you take particles or you take other galaxy clusters, there's no inherent reason why we should be able to observe either of them. But we've built additional instrumentation that's allowed us to make those observations. Likewise, even if you consider computers, there are many kinds of calculations that would be almost impossible for humans to get right, or at least it would take a long time, and the chance of error would be very, very high if you're doing it by hand. So, I mean, humans are becoming increasingly cyborgic, and we're able to outsource cognition to computers. We're able to outsource vision to microscopy and telescopy. I mean, we are able to do things with technology that we couldn't do before. So the ultimate question there is, if there are fundamental, physiological limits on our ability to understand certain aspects of physics, with expansion of the kind of instrumentation apparatus at our disposal, and then using that, in concert with perhaps computation-assisted science and mathematics, can we, with time, come to appreciate structures and even maybe forms of things like computation or things beyond computation that are increasingly sophisticated, and gain, more verified understanding of observables, and with time, expand our own understanding of physics and physical systems without us. So Lukasz's point, I mean, can the cyborg human eventually confront the Lovecraftian, sublime thing that we can't fully, understand?
I mean, where are the limits? How absurd must something be for people not be able to comprehend it?
Well, but here's another thing, right? I mean,
some limits, right?
Well, okay, but we shouldn't give. I don't think we should give too much credence to Lovecraft, because I mean, there's no a priori reason to presume. This is the other difficult thing. It's tempting to presume that the things that which human observers can't capture is some sort of sublime, numinous, absurd thing that's very difficult to understand. I mean, Lovecraft is, I think, including this as kind of a rhetorical provocation. It could just be that it's, that we've kind of, in a coarse-grained way, captured the quintessence of what there is to understand the physical system, but there are many small little details that we haven't been captured yet. Or it could be that the main surprise we haven't seen yet. This is unknown. It's not clear because we don't have a good sense of how limited we are.
Well, kind of this notion of computation move because it's a very general definition, and you can always move the goalpost and redefine what we mean by it. And as soon as we encounter something absurd, we just redefine our notion of computation immediately and just embrace the new absurd under the same framework. That's how math works, it seems to me. It's like everything that we can describe, as soon as we think of a question that maybe there's something else that math and mathematics is unable to describe, we just redefine what we mean and expand the definition of mathematics and how much it can handle.
Yes, right. I mean, this goes back to this whole relationship between mathematics and computation thing. And I think one aspect of computation, that this is probably why Stephen is in part excited about this whole multi-computation thing, is that in part, computation, as soon as you try to view it more abstractly, as you would with mathematics, it is some particular, path of executions or rewrites or substitutions or something. With multi-computation now, the idea is to actually consider several of these. So this is kind of an example, maybe of what Nick is even suggesting, which is if you take an almost mathematical mindset, you could just continue to expand the definition of multi-computation. From there, something that I've thought about before, but I've kind of abandoned because I couldn't come up with an actual way of making it precise, is you could imagine even in the future where you have, different paths of computation, and then if you're actually considering like homotopies between these paths, which is something that people have tried to consider before, is, are those homotopies themselves computations? And then in this case, you have basically computations between different threads of time, which is difficult. I found if you really want to make it precise, it's very difficult to actually capture what that means computationally or mathematically. That's an example of a kind of a challenge. Like, what would it mean to actually compute between different threads of time, or to get higher and higher? Higher paths of computation seems very alien to me and very difficult to understand. But yes, I like this notion that Nick has, which is that computation is not fixed in its definition. We could just continue to expand and amend it in order to have it kind of consistent with whatever we think the frontiers of science could be or are at the time.
Yes, it's very hard to imagine something more general than that. It's pretty simple, right? It's not like we had in some 17th, 18th century universe made of clocks and gears moving the universe. At that time, you can imagine that there's something else, but at this point, if you at such fundamental level, it's just abstract computation and rules, there's like no going further.
Well, what do you think the people said in the 17th century about clocks and gears?
I think, imagine if they had the similar conversation like we're having, they could easily imagine something more fundamental than that, but no longer at this point.
Yeah, but they could, like, you can simulate all the computation with clocks and gears.
But they're not like very abstract. They kind of, oh, you see, maybe like basically what we did, we just generalized our notion of computation.
People didn't think of literal gears, right?
Yeah. But still, maybe
we don't think
expanded
of
the
literal
definition.
computer.
Oh, hey, we should not neglect Carlos. Carlos had two comments. Okay, I'm going to narrate on behalf of Carlos this time. And for first-time viewers, Carlos doesn't sound like this. Okay. Yes, but electrons need not all be interchangeable. I really cannot think of any other example of something in nature that behaves like a data structure. This is one comment from Carlos. Second comment is, I think that one of the key aspects has to do with discreteness and finiteness. Intuitively, reality seems continuous in pretty much all empirical channels that are not human-centric, like language. The emergence of discreteness seems to be a discovery of evolution at different stages. To me, the surprise is that fundamental physics has very similar patterns to to the data structures we have developed at our human linguistic level. That's interesting. That almost gets us to the analytic. That almost gets us to this kind of analytic synthetic distinction in philosophy. But if I understand what Carlos is saying, like ultimately we have to actually fashion these concepts. We have to actually be able to discuss physics in some way, or any scientific discipline in some way that's actually amenable to human language. And human language is discrete, and it's also, depending on your view of linguistics, also this kind of computational process. Um, well, I don't know. Is the idea, Carlos, that mathematically it's not too difficult to express things in continuous terms, but linguistics has a way of forcing things into a more discrete setting? Okay. Well, okay, so let's go back to this. Ah,
Only symbol.
Nick?
Oh, I don't know. The language is human language. It seems like just another instance of computation. It can be also extended indefinitely. So I don't see any like contradictions and philosophical problems here.
Well
There are
then,
single
okay.
patterns everywhere. Yeah. This is like it's just. I mean, there's no surprise to me that there are similar patterns.
Well,
So
I guess
the contradiction,
okay.
but no surprises.
Well, so one thing we brought up yesterday is if you consider computationalism, for lack of a better term, as naturalism, then what would be supernatural? Like when you're thinking, if you're trying to develop a naturalist theory, you're trying to avoid reliance on anything supernatural, just natural explanations. So if you're viewing nature as anything that's computable, then the kind of naive thing to say is that basically a naturalist theory is a theory that's completely computable and doesn't rely on anything that's hyper computational. So I pointed out before that like questions of the reals, maybe questions of the continuum, these things seem to be, when you're in danger of employing things that are not readily, say, Turing computable, then maybe you can't rely on this as being natural. Though I still fear, this is kind of what I was getting back to before, is that as soon as you describe computation basically as nature, I don't know, unless we're going to start to get into some loops, some self-referential loops, it's still not clear how you make the leap from computation describing certain behavior to actually saying that basically you can view natural behavior itself as computation. This still goes back to what is the origin of dynamics and what are the origins of rules? If you really take seriously that, you could basically view nature as computation, as the evaluation of certain rules. Where do rules even come from? Why are they possible? why is it that things that are these possible relations between things, they actually become actualized? It seems as though if you treat nature as computation, that there's no computational answer to why those things happen. That seems like a limitation. And again, I'm not saying these things to be cruel, or I'm just trying to understand, like, is this naturalism or is it something else? Can you basically treat computationalism as naturalism, or does that fail because there are certain limits that computation itself can't explain? Mukash is smiling.
I like how it's visible what Carlos is typing on the stream. You can.
Carlos says, I think rules are the human component of a computational system. In a sense, the system just works, and a human is what understands the working as the action of rules. Well, right. It's still not clear where the action comes from. I think that's and why the system just works. It's the other thing. Carlos says the action of the system just is, in my view. Well, yeah. But it means it's not. It means it's not explained. I don't know, Nick. I mean, Nick, can you make some sort of argument as to, if you even take pattern matching or substitution or something, can you make some sort of argument as to why, essentially, pattern matching substitution is such a natural thing, and that it's basically inevitable? Let's just make this argument. Like, you take a universe in which you have patterns, but the patterns aren't getting matched, versus, why is it that these things are basically, there's no choice but these patterns to get matched? Now that we have this molecular pattern matching, it's almost like, you put certain chemical compounds together, and they're just going to react with one another. Some similar kind of argument that basically patterns inevitably have to get matched. If it's not inevitable, then it seems quite difficult to presume, to explain why it is that computation kind of proceeds.
You don't have to have patterns necessarily, right? Just
no, but I think it's a kind of a good example. Kind of straightforward example.
I don't even think that if you make something just is, like Carlos says, you have to justify of its existence every time. Unless there's always going to be this infinite power of why questions. It's like you either stop at just is and stop questioning any further, or I don't know. Otherwise, you just never stop answering.
Or like circular definition.
Yeah. So I don't think there's a need to justify the existence of rules and patterns and computations. So like all this just is.
Guys.
Because we're not constraining it. You can always say for something that just exists when you don't constrain it. If there are any constraints, you can always ask why such constraints. But if you don't impose any constraints, then totally fine for it just exist. I don't know. Platonically.
Right. I think it's just not fully maybe we can rephrase what Nick is saying as maybe this pursuit of naturalism is not as important as you might think, because ultimately there are going to be certain things that you decide not to explain with your theory, and those things kind of lie outside of explanatory reach of your theory. And Nick maybe thinks that there's no way that you could ever boil everything down to things that are actually explainable in your theory, where you're not relying on something that's explainable outside of it.
You just have to stop at some point, and as soon as you stop it, the better. You don't have to make a very long chain of whys.
I like asking why. I mean, as Wukash said, he said in some previous conversation, you either have some infinite tower of turtles, or you have some sort of self-referential loop.
Which is kind of the same.
It's kind of the same thing, but I think the human observer provides some opportunity to build some self-referential loop that's kind of interesting. Like there's some sort of observer theoretic explanation for some of these things that's probably on an anthropic level kind of mature and self-aware. See, that seems to be some way of being able to overcome some of this, which is why does this exist? Why does this exist? Why does this exist? Well, in part, it's these are concepts that arise at the interface of the human observer and the physical system. These are explanations that we give, and we can't, at the moment, speak to their a priori existence because we don't know. There's something like that where instead of just saying we're not going to answer these questions, we're just going to accept it as is. It's probably some finer way where you can say, well, basically, we're going to accept them as elements of this physical theory that humans have, and it's basically unknown whether or not they have some a priori existence.
Okay,
you see, I mean,
Carlos says circular definitions are good because they point to things that should not be justified beyond just is. And the art of mathematics is to find all the elements that should fall in a single circle of definitions and how circles relate to each other.
Interesting provocation. I mean, one basic question is, again, if you take a modest anthropic point of view, like who are we even in a position to be able to determine what is natural, what is beyond nature? I mean, to say we have this naturalist framework and we're able to explain nature solely in terms of everything that's available to nature, and we don't rely on anything outside of nature. I mean, again, our scope of what is of nature is going to be somewhat limited at the moment. And so, it could be the case that you have some theory. The theory still has certain aspects of it which can't be explained internally, but find well that there are probably many things you don't understand at the moment. So your picture of nature is going to be incomplete. So this notion that you're not going to rely on anything outside of your understanding of nature, I mean, it seems as though perhaps that will never happen because our full understanding of the natural world is never fully mature. It's like almost like in politics, they talk about like the end of history. If you had a full view of nature, it'd almost be the end of science because there would be nothing else to figure out. And then you'd have you'd have full kind of theory closure. Right now, our theories don't have any closure, but it seems to me that's because science itself has not been fully accomplished. I'm becoming more wary of this naturalism thing. Maybe naturalism is not something to aspire to. Oh, David. Well, David, my voice is kind of messed up today because I'm sick, so I'm narrating everyone the same way. This is how Carlos sounds, this is how David sounds as well. Okay, so David says, the idea of the universe being computational reminds me of believing that the universe is inherently mathematical. It seems you are all interested in understanding what the minimal structure is needed to construct the universe. But in order to answer that, I think we have to first understand what the universe is, or at least a good idea to some approximate level. Otherwise, every proposal seems to be a conjecture that needs to be demonstrated. Well, the only question there is, in order to even be able to express our understanding of what the universe is, we either have to describe it in somewhat informally in human language, or in mathematical terms, or in computational terms. So
what's surprising from the physics project is that it doesn't matter what are the actual computational rules. Some features of the physical universe are common to all of them, right? Like relativity and quantum theory. That's the point, that we can find it in any part of the Ruliad. You have these features. So at least these two properties are very general. And that was the surprising thing that we have from the physics project.
Look, I mean, the functionality we have right now for modeling special relativity and quantum mechanics is still somewhat elementary. I mean, I still suspect that as these models become more specific, that it should be the case that some rules happen to give rise to universes or the physical systems that happen to be similar to those that we see, and others won't be. I mean, right now Nick, I mean, come on, let's be frank. Right now we have these causal graphs, we have branchial graphs, and there are certain interpretations that are coupled to that. But quantum mechanics as a full theory is quite specific, and
that's why. Well, it's very problematic. That's still you have quantum foundational research, so people are quite uncertain what is actually specific or not, right? But to me, it seems like it's very inherent feature for all computation.
My fear is that if it seems as though any given rule will give you these particular physical theories, that it means that they're not being defined with enough constraints, or that our understanding of them is too general. I mean, if it's the case that that you have this definition, multi-computational definition for relativity and quantum mechanics, just that any given rule happens to give rise to these features, I mean, that seems to me that they're just unconstrained and not precise enough, right?
Well, not every, maybe universal set, but it's not hard to imagine rules that give rise to those features.
Well, it's not hard to imagine rewrite rules that give rise to causal graphs and branchial graphs. That's true.
Yeah.
Many of them have those, but that's just the first step. I mean, look, a causal graph is a certain model that we're using, not unlike what they use in causal set theory in order to describe, in order to try and describe relativity. But as we're seeing, even as we work on this, that in order to actually get space-time that has the properties that we're looking for, I don't think every rule is going to satisfy that. And I think that as we get more specific about quantum mechanics and maybe field theories, et cetera, it's also going to be the case that it's going to be some small number of rules actually satisfy it. Otherwise, it seems as though
there's no way to not satisfy it. It's like we're not posing any constraint on the rules or computations in order to derive notions of relativity and like quantum theory, how we see it in the physics project. So yeah, and as David says, if the Ruliad relates to the space of all possible computations, is the claim that all possible computations have quantum and relativistic properties. And I think the claim is yes. It's like all possible computations have those.
I don't accept that. That just seems ludicrous. I mean, it just seems stupid. Like
maybe
it seems so arrogant to assume that any possible, like we're trying to have some project where physical systems are being generated emergently by certain computational constructors. And if you just say that any possible computation is going to give rise, you can plug in any particular initial condition, any particular, rewrite system, it's going to give you quantum mechanics and relativity.
Well, I mean, again, not every, but like they may be purely relativistic, maybe purely classical, but it's like without posing any more constraint, if you just enumerate all possible rules, at least you can certainly say that there is going to be relativity in quantum theory, because rules can be run in parallel and rules can overlap. It's like that's all the consequences of those that we have those theories in physics.
I don't think the claim is really justifiable until we have a until we have a actually rich interpretation of relativity and quantum mechanics. I mean, right now, again, I mean, branchial behavior. I mean, you can make the claim that there's something quantum about it, but there are many aspects of quantum mechanics that we do not have a good interpretation for at the moment. Likewise with relativity. So why make this claim? I mean, part of the philosophical discussion is,
Well, it's a hypothesis. Okay, that's very. I don't know. I personally like it, and then there's no immediate reason to drop it. It's like I think it should be pursued further. We can develop the actual intuition how everything arises, and yeah. So.
Well, this is Carlos Mukash. This is a debate that goes back a long time. I think there was some debate about this during the last summer or winter school, where I've for a long time held the suspicion. Why should it be the case that any arbitrary and Nick is saying it's not any arbitrary computation, but why should it be the case that quantum mechanics and relativity are basically common features to literally any given physical system or universe that you could construct with some arbitrary rewrite rule? It seems to me so presumptuous to assume it. Again, it could be the case that a causal graph or a branchial graph is these are very general properties of data structures that might appear often, but acquire different physical interpretations once you have a more specific, nuanced view of what the physical interpretation is. It seems to me too narrow-minded to presume, okay, let me put it this way. There's a mapping in this direction, which is it seems as though branchial graphs could describe quantum mechanics well. That's fine. Basically, we're going to use branchial graphs to describe things that appear quantum mechanically. But then to go the other way, which is to say, thus, whenever you see branchial behavior, this is quantum behavior. Therefore, any given physical system has quantum behavior. It doesn't seem right. This is like map territory confusion. You can use specific computations over your data structures to describe certain aspects of your physical system, but then to forget that this was originally just something that you used to model it, and then to say, well, look, we're modeling it this way, thus this is physically what it is, and anything that admits a causal graph this way, or anything that admits branchial behavior, therefore is quantum mechanical or relativistic. This seems to me wrong. It's just something that we're using to describe it. And maybe it's the case that in alternative physical systems, there's very, very different kinds of behavior where, yes, there are branchings, different things can happen in possible instances, but maybe it's not quantum at all. Maybe it's something completely different where there's also alternative possibilities, but they're not actually quantum. In principle, you can imagine it. I mean, I don't know. I tend to approach things with a very large degree of skepticism and presume that in the realm of all possibilities, there really is quite a bit of variety that you can imagine.
Well, quantum theory has a variety computationally. I think there's always like a spectrum of quantumness that you can describe. You can imagine like toy models that go from classical to quantum theory almost, and even beyond. So how much you can describe the actual correlation between your measurements, right? And the fact that we do have the quantum theory that only sits somewhere in the middle in the spectrum may be an actual fact of the specific instance of the rules that we experience, but the underlying mechanism how all of it basically is being constructed from just branching rules. Maybe that's the generic feature of all of those theories. It's just because the spectrum only arises when you have the actual measure of correlation. So maybe the actual quantum mechanical axioms that we have is a single instance, but the branching in general can describe all of them. So this is yet not unclear, but I think there's some deeper problem into it. I don't know. That's what we're trying to solve here. So obviously we can't answer immediately how everything interconnects.
No. I think personally, I think the thing that I find frustrating is there's all this research to do, and then there are also just a bunch of claims that kind of sit on top of the research that we're doing. And that, to me, it just is unnecessary pressure. Like, why have all these claims circulate that the theory does this or it does that when the research is still at such an early stage? Just in terms of the way that we interface with people as an institute, I think we should try and develop, some set of conjectures or things that we either agree about amongst ourselves or disagree about, but kind of certain questions that we want to answer. Because, I mean, I find it in my correspondences with people all the time that people do pay attention to like things that we claim about the models or don't claim about the models, and often they're like claims about which not everyone agrees, or claims that were made like years ago, and it's a somewhat difficult environment to do research in. It's usually, I mean, yes, there are claims that are made in sciences all the time, but I don't think it actually helps foster wider discussion of the kind of research that we're doing. It's like this weird case where, in some sense, a lot of it seems settled, like, oh, we have quantum mechanics, we have general relativity, et cetera, et cetera. But then when you poke it even slightly, it's like, oh, but actually we're doing very minimal modeling still on these various areas. And like those two statements are very difficult to reconcile. I think there are some more things from Carlos and from David. I'm going to narrate them in the exact same way. Okay. Carlos. The implication is that this is obviously false, though. There are clearly computational frameworks that are neither quantum nor relativistic. Okay. Carlos says, I will not claim anything about quantum mechanics, mostly due to lack of experience, but for relativity, there's something quite deep about the structure of unbiased observers sharing measurements in an objective shared universe. Okay, David says, for instance, Newtonian mechanics is neither quantum nor special relativistic. Additionally, one has the freedom to hypothesize that relativity is wrong and that the laws of physics are not symmetric. One can compute results in these wrong theories. Therefore, if the Ruliad truly describes all computations, then it can describe computations of wrong theories too. Yes, yes. This is the view that certainly the view that I take. I mean, any given theory should, or many theories should be able to be simulated in some way computationally.
Well, not all theories
some
are event-based. It's like the claim is that relativity, as soon as you base your theory on events and their interdependency, you get relativity. But like Newtonian mechanics is just it's a simplification, or maybe just approximate results that an observer can experience and recompute, but it doesn't have to follow the same causal relationships. I don't know how to explain it, but it doesn't seem a contradiction that you still can have simpler and wrong theories, but they're not gonna be inherent to the actual Ruliad or event-based theories, right?
Well, but this is not a definition of the Ruliad that I've seen before, which is it's actually the space of all event-based. This is a huge constraint on.
No, it's not a Ruliad. As soon as you take a path for the Ruliad, you will reconstruct the causal effects and causal effect relationship between all of those events. Right? You take the path, and as soon as you take it, the most general description would be that you have a causal graph and relativity and branching and quantum theory. But if you actually consider a single observer in the same event-based theories, and within perfect model, like Newtonian mechanics, it can perfectly do the same kind of computations with the events that no longer follow the underlying evolution. It's just simple single way, or whatever computation the observer will actually compute in order to derive some prediction and results. It doesn't contradict.
But Nick, I mean, but still, I mean, let's say you have some causal graph. I mean, let's not be dogmatic. A causal graph seems to be a useful tool for modeling relativity. Saying that we just get, say, special or general relativity every time that we have some rule that it's a causal graph. I mean, there are many actual features and requirements need to be satisfied in order to say we actually have general relativity. I mean, if it's so simple.
It's like it's like already proven that all you need to do in order to derive the general relativity is just order. So causal effect relationship. Nothing, no further axioms are required. It's like, right? You have order, transitivity of this order, basically the theorems, order theory axioms, and you get general relativity in the limit. And order arises by just following a path through the Ruliad. So basically, we can't provide you a theory of everything, but at least this meta theory framework for general relativity and framework and quantum theory. That's like the minimal claim that the physics project have. Even if it's impossible to go further, then at least that's the consequences of that computational thinking that you have in general have relativity and quantum theory. But beyond that, you have to be more specific. But also the most general features that you have, just given the computation alone. And computation is given by just following this very abstract notion of the Ruliad. As soon as you instantiate it with some parameters and choose a path that the observer follows. And it's just purely platonic. Every path is possible. It's just none. Yeah. What else?
We have another quote from David. David, it's important to at least be clear about conjectures and hypothesis versus proven results. It is a challenge, though, as initial evidence is found and a summary of the result is provided. It becomes difficult to clearly state the result in short terms. Well, yeah, I agree. I should go back and look at the early work that Jonathan did on relativity and on quantum mechanics. I mean, this is something that we really should have a better inventory of, like the claims that kind of attend the research that we're doing. How many of these are conjectures? How many of them are basically just speculations? Which of these, agree with claims that are made in other theories of physics, et cetera, et cetera? that would be very helpful. I would find that very helpful. There's another thing from David. David, thanks for your participation, by the way. David, one can construct non-quantum and non-relativistic event-based theories that are not good approximations of nature, yet those would be computational. If the Ruliad can describe the computation, then not all computations from the Ruliad are quantum or relativistic. One can write down an infinite number of different theories that have order. For instance, isn't Gorad's work hinting at Lovelock gravity more than GR?
I'm not sure how you can have non-relativistic event-based theories. Like you would just have a single. You basically constrain your events always to follow each other. It's like you don't have to. There's freedom of order of events so that they can be run in parallel, and you have this freedom of reference frame that you can take. So I'm not sure. As soon as you have event-based theories, maybe David means something else by events. But the short answer is that you can choose a different path, and obviously different paths would be in a less of like there's going to be less degree of branching, so it's going to be less quantum this way, maybe non-quantum at all. But it's still a valid theory. It doesn't contradict, but that there is some paths that don't have any branching. Sure, it's also computational. It's just not a feature of this particular path.
Well, I wish we could have some sort of more real-time dialogue with David, though. Maybe he'll respond to Nick's question in the chat. We might have to wrap up somewhat soon. But Carlos, Wukash, I mean, this has been kind of a conversation now between Nick and David and I. What do you two think about all this? Especially this relationship between, we have. Well, okay, no, you followed the conversation. What do you think about, what we've been discussing?
The general framework of special relativity is pretty universal. Like as soon as you have causal structure of any kind, you get something like that special relativity. You can constrain yourself to some limiting cases like Newtonian physics with absolute time. And then, this is computational. I guess you can computationally model Newtonian physics and you don't get the relativity.
Yeah, that's the observer that's doing the computation, right? Whatever observer is doing is completely arbitrary and doesn't have to take anything into the actual events that surround him, right? It doesn't have to do anything with it. So the observer can have any model because the observer lives also in the Ruliad and also can follow different paths in a way, right? It's just maybe the actual state of the universe he lives in instantiated in this Ruliad is not actually the same, posing some kind of constraints. Oh, that's complicated. We should formalize it a little bit more, this philosophy. Pretty hard to talk about it. Just
yeah. Well, I think. I mean, we've had this student at the winter school who's interested in the philosophy of some of this stuff, and I would very much like, to take some more time to kind of account for more carefully, like our presumptions and our interpretations and why we believe certain conjectures or hypotheses to be true, what we can actually do to better pursue them, which things about which we're uncertain. All of this would be very good. Because I mean, this research is now a few years old. We've learned things, new perspectives have emerged, but there hasn't been that much like kind of theoretical or conceptual work on this physics research for some time. And I think, you know, as the institute, we should be doing that. So yeah, that would be great. Some sort of piece. Maybe it should be in our first thing that we distribute to people. Some sort of kind of piece conceptually going through what our positions are on this physics research. That would be very good. And again, I mean, one thing that I'm trying to do with this discussion as well is that I very much encourage, even at the institute, like disagreement and debate and challenging one another. It seems really important. There's only so many of us, and the research is young. So if there's any kind of dogma that becomes instilled amongst us, then we're really going to be in trouble, because then we'll have very few people who can actually push back. So I'm trying to at least take responsibility for challenging Nick. Nick's a very capable, steady, calm person. You know, trying to kind of challenge each other to fully kind of defend or explain these claims, because we're kind of responsible for this very early stage research. Okay, one thing from R. Marks 88. On a slightly different note, is there or could there be a rule that describes how rules evolve, or classes of rules evolve, so that if you know one rule, you can know every other rule above or below as a consequence of a given rule? Well, you can certainly generate rules computationally. That's not too hard. Now, whether or not you could develop a rule that can predict how other rules evolve, this is where this whole computational equivalence, computational irreducibility thing comes into play. You know, for some rules, you can develop a rule that can kind of gain some predictive power over it and guess what's going to happen with it. In other cases, at least at the moment, we don't yet have a way of being able to predict what happens with certain rules. This gets into a whole other issue of this question of computational irreducibility. Actually, again, relating computational irreducibility back to the things that we've discussed before, you know, it could be the case that eventually some of these things that appear irreducible, we do find a way to gain some predictive power over them. Maybe in some higher, more sophisticated mathematical setting, some of these computations become more predictable. Like, I don't know, maybe in some non-Archimedean blah 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 blah. So, some of this behavior actually becomes much more simple than you would think. So this is also kind of a, I don't know. We're still somewhat limited in human history. So many computations appear to be entirely irreducible. I still maintain the presumption that maybe with time, some of them can be made more reducible. We don't know. I guess that's part of science in general, is, you know, this enterprise to make certain things reducible. And for things that can't be made irreducible, or for things that can't be made reducible, that's where many of these techniques that Steven has suggested kind of come into play. All right. Well, this has gone on. Yeah. Well, no, I think we kind of started a little late, so this ended up being like a full hour stream. David, thanks so much for your contributions, as well as to R. Marks. Thank you, Carlos, for being for typing out all these answers, and Nick and Łukasz for a series of provocative, interesting remarks. We should have these conversations much more. It's kind of a shame. Like, often I feel like we'll have these debates and there'll be things that seem unsettled or I've wanted to talk about before, and I realize I haven't actually spoken about it for like 6 months. I have to find some way to, like, you know, take these really fundamental ideas and discuss them enough until we start to agree or understand, or achieve some common agreement or understanding, though a non-dogmatic one, where I think it never fully stabilizes. We always still find a way to challenge each other and really make sure that we know what we're talking about.
Thanks.
All right, guys. Yeah, thanks, guys. All right, well, I think for at least Nick and I, it's basically back to the winter school. Yeah. All right. Thanks, everyone. Cheers. See ya.